Now, since the start of a new part, let's just, an example of a vector field. Example of a vector field. Just pick another one just as an example, as a reminder. It's just a thing that has multiple inputs, maybe like, x comma y, and then the output's going to be a vector. Maybe you've got x times y, and then you have x plus y squared. I don't know, something like that, right? So that's an example of a vector field. Let's get two examples. How about also a three-dimensional example? So f of x comma y comma z equals angle bracket xy comma x plus, let's have fun, z squared comma 3. Let's just not even use any variables in the third component. Why not? Okay, so we have two examples of vector fields here. Now we're going to talk about the other major topic of this section. So this section is called line integrals, and we've talked about line integrals of scalar fields. Now let's talk about line integrals of vector fields. Just treat them as totally different creatures, to be really honest. That's the best thing you can do. Okay, just new concept. In some sense, it would have been better if the textbook author had split it up and this was the start of a new section of the book or something. But almost every calculus book doesn't do that. So I think it'd be better organized as a new section. Think of it like we're just starting a new section. Here we go. If f arrow is a vector field. Okay, so like for instance, it could be this or it could be that. Just using the examples above. So let's just clarify again what this is, or say at least a little more detail. I guess we'll just say up here that if the inputs are points x comma y in two-dimensional real space, then the outputs are two-dimensional vectors. And if the inputs are points x comma y comma z and belonging to three-dimensional space, then the outputs are three-dimensional vectors. We already see that pattern here. Yeah, there was two inputs here, two input variables x and y. So this vector was a two-dimensional vector. Okay. So all right. So sorry. Continuing the setup. If f is a vector field, and the parameterization of a curve C is recorded in a vector function, r arrow of t equals angle bracket x of t comma y of t. Okay, so the information of a parameterization for a curve, remember a vector function is very much like a vector function, but it's really recorded in the format of a vector function. So either like this for the 2D version, or r of t equals angle bracket x of t comma y of t comma z of t for the 3D version. Okay, for a less than or equal to t less than or equal to b, then, so that's the setup. If you have that stuff, so you need to be provided a vector field, you need a curve, and either the curve is described in words and you make the parameterization, or the parameterization is provided for you and you make a vector function. In the end, you need a vector function, whether it's a 2D vector function or a 3D vector function. Okay, so once you have that, then the line integral, the new thing we're defining here is the line integral, new kind of line integral. The line integral of this vector field. Why is this new? Well, up until now, all we've talked about is the line integral of a scalar field. So the line integral of this vector field over the curve C is, well, so first of all, here's the notation. Integral sign over C. F arrow, so capital F arrow, or you'll see in the book a bold F, dot, dr with an arrow on it, equals. Okay, so some comments are already in order here. This thingy that's right there, all before the equal sign, this is the thing we're defining, right? We've defined it in words right there. This is the notation. And let's just clarify again that there is a dot. You have to draw the dot. You have to draw the dot. This little r with the arrow on it, either it's a bold little r in the book or it is an r with an arrow. The arrow is required. You have to draw the arrow. Otherwise, just the things that we're doing in this chapter, you really have to keep track of a scalar versus a vector. Otherwise, it's going to be complete madness. Okay, what is this equal to? It is going to be the integral from t equals a to t equals b of vector field of this vector function, the one that was built out of the parameterization, r of t, dot r prime of t dt. Okay, so this is notation, but if you need to practically compute it, then you set up this. So this is to compute. A couple other comments. This part right there, we should comment that this, it's a bit of a shorthand notation on its own. This is f, the vector field, applied to the vector function that represents the parameterization of the curve C. This is really just shorthand notation to actually, what it really means is you take this vector field which has 3 inputs and you feed in the specific parts of the parameterization. Okay, so this x of t, which is really literally taken from right there, or I guess right here. And if it's a 2D version, then you leave that out as you might expect. Okay, and just some comments that would be important to mention off to the side here. So dr, which you're seeing right here, let's circle that, right, is equal to r prime, let's write that cleanly, r prime of t dt, or another way to write this is dr is, with the arrow on it, is equal to, another way to write this derivative. This is that derivative we've done for vector functions a long time ago. It's not a bad derivative to compute. It's just one component at a time. But it's dr with an arrow over dt. And at least in this notation, again, it looks right, as if the dt's canceled as far as trying to remember what it means. But the point is that the dr circled here in blue, it's here and it's there, and that's this or that, and so that's this right here. So the point is this turns into that. We will, of course, talk about setting this up and going through examples of the computation and so on. But before we do that, let's take a little sidestep into just talking about what the heck is this actually computing at all. And to address that in the next part, there's going to be a huge discussion of dot product. Okay, the fact that there's a dot here and that dot is really just carried over right there. Look, this is really going to be a vector, right? Because this thingy really outputs a vector, since capital F is a vector field. You're going to take a vector and dot it with another vector, and that's really the key thing, is that we're about to talk about. Maybe I should box this part in green. We're talking about an integral, which is really just a fancy way of adding things up instantaneously. We're adding up many dot products, and so that we're going to talk about what that would mean in terms of interpretation, both in the science standpoint and just kind of mathematically on its own as well.